Good, good afternoon, Katie. Good afternoon, Maria. Good afternoon, Alexis. Very good. You guys are, this is a very on time group. I appreciate it. Good afternoon. Okay, you're ahead of me. And there's Paulina and Claudia. All right. Good afternoon. Good afternoon, Maria. Good afternoon. Good afternoon. And Shy. Good afternoon. Hello. All right. This is happening. This is totally happening. What happened to the chat? Okay, I'm going to do the hellos quickly. Wait, what did happen to the chat? Is the chat gone? Hold on. We need the chat, don't we? Okay. Yes. Good afternoon, Katie. Good afternoon, Maria. Good afternoon, Alexis. Good afternoon, Emily. Hello, Jenna. Good afternoon, Shai. Good afternoon, Jada. Good afternoon, Logan. Good morning, Shirley. Good afternoon, Brandon. Good afternoon, Claudia. Good afternoon, Stephanie. Afternoon. Right. Okay. Yes. Good correction. Shirley. Okay. Oh, good. Okay. Let's see. Yes. Okay, let's get straight to it. Josephine has so I will do my best. Yes, let's prioritize Josephine's specific question. Let's see. I will try to answer it concisely or clearly as I can. So yeah, go for it, Joseph.
Okay, so for question one, the plushy one on the practice exam, when it
yes.
says, so I tried this problem for a really long time, and I got hung up on the fact that it was being thrown upwards. And I was wondering if this is like a correct way to approach the problem. When it says in the problem that the plushie is being thrown upwards, is that just so that you know it's going to be acting in the y axis and not the x axis?
This is a great question. Okay.
And like the way that it's being thrown up is negligible, like that distance.
Wait, okay. Great question. It re it okay. So to be totally honest, it's not net. It is really going up. Like that is actually information that it's as opposed to the answer and the problem would be different if the thing were being thrown down. Let me just say again quickly to everybody. This is a great question. This is question number 1 in part 1A. In fact, let me see if I can quickly do well. Okay. Well, here, let me do. I'll see if I can do quickly do this. This is a perfect kind of question because yes, if I don't lose my mind, I can do this. Yeah, because this won't take up a million. And I'm sure Josephine's not the only one concerned about this. So it actually does make a difference that it's going up. If we said it was going down, it would actually be a different answer. But here's the catch, or here's I think the information you're looking for is it will make a difference in the answer. And the amount it goes up is not negligible, meaning it's not small. Like it actually might be large. And it should make a difference in the way you picture the problem. It actually, hold on, someone's coming. 1 second. It actually is like going up for a while, slowing down, getting to 0, and then coming down. All of that is actually true. So what you're thinking about it, like that is hard. I mean, like you're right, but here is the answer or whatever. Well, actually, I probably in a minute can literally do it. But here's the key: is that as long as you are consistent or careful with positives and negative signs. The key to this problem is that displacement means final position minus initial position. Displacement is the difference between where something ends up and where it starts. Displacement, like remember in homework 1, if the instructor's standing here at +4 and the instructor walks all the way to -1, let's say, or yeah, if the instructor walks all the way to -1 and then comes back to +2, right? His distance might be really long, like, oh, all the way to -1, that's 5. And then back to +2. Oh my God, that's 3 more. That's a distance of 8 or something. But the displacement, so bear with me for a second, the displacement of the instructor, say in homework 1, when the instructor does something complicated, like go that way and then come back, if he starts at +4 and ends up, I don't even remember what I said, but say ends up at +1, his whole displacement is merely just -3. It's just like where he ends up subtracting where he started. Why I'm saying all that, it sounds like I'm saying a lot. It sounds like I'm making it harder. But here's why the problem is easier than you think. If you use the equation y equals 1/2 at squared plus v t, or x, whatever you want to call it. But like we're in the vertical axis here now, so I'm going to call it y. And here's my main point, definitely to Josephine, but to everybody. Like the way to do the first problem on the exam is write down the equation. I mean, write some explanations and stuff like that, like do the 5-step method. But the key equation for this is y equals 1/2 at squared plus v naught t. Okay. And again, or you could technically say y minus y naught, but we could say that y naught is 0 here. Like the thing starts, wherever this thing starts, we can call 0. Wherever it's starting, you can call position 0. Okay, you can write down that, and so cross out the y naught term. So you write down the equation y equals 1/2 at squared plus v naught t. I'm just calling it y because we're in the vertical axis, like Josephine said before. And here's the biggest key of all, and I will repeat this in a minute. At least I'm going to make sure with Josephine that she's clear, and anybody, because it's a great question. Here's the key. If we in our diagram, like draw a little diagram and say, okay, I think up is the positive direction and I think down is the negative direction. Like I'm labeling directions because I think both directions are definitely involved in this problem. I definitely have to make a choice. So say we call up positive and down negative. Here's the key. That equation, y equals 1/2 at squared plus v naught t, that equation is talking about, is referring to y as a displacement, not a distance. It's a displacement. So when you go to plug in numbers in that equation and solve, you're solving for v naught, right? When you go to plug in numbers, if down is negative and up is positive, if you plug in a negative number for the acceleration, like -9.8, or even better, -10 meters per second squared for that acceleration, and you plug in a negative number for the displacement, like you plug in -150, right? I mean, I'm saying too much. I really should just do the problem, and maybe I will in a minute. But like, if you're standing on this building and you're calling the top of the building where you start 0, even with your picture, even if you draw like da, 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 goes up and then da, 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 comes down, the whole displacement at the end is that the plushie is going to end up 150 meters below where it started. So you plug in -150 for your displacement, you plug in -10 for your acceleration, and assuming I didn't screw up the numbers, which I don't think I did, then and you plug in whatever it says for the time, you plug in 10 for the time, and just do algebra or whatever and solve for v naught, you should get a number for v naught that is positive, meaning it was thrown up. And that will be your answer. I'm going to say one more thing, and I'm going to shut up, and I'm going to literally check in and make sure this is the key point is as long as the sign of the 150 is the same as the sign of your gravity number, which I recommend just calling it 10, like the meters per second, the free fall number. If those signs are the same, then the math will take care of all that amount that went up. So you even could call down positive if you want, and call up negative, and you could even make 150 positive and make the 9.8 positive, and the numbers will work out, and you'll end up getting a negative number for your answer. But in that system, negative would mean up, so like you'll still get it right as long as you're clear. And the bottom line I'm saying, and then I'm going to make sure Josephine is cool, or anybody else. This is a perfect, I mean, of course, I'm already talking too much, but it is a perfect kind of question to ask today. What I'm really saying is the amount that the thing goes up, it's not negligible. It's not like so small that it doesn't matter or something like that. But what it is an amount that you never actually have to figure out or worry about, because the equation totally takes care of it, because the equation's about displacement. So the way you tell the key point is when you plug in the 150 and the 9.8 or the 10, as long as they are pointing in the same direction, like the math knows. Okay, I'm going to stop for a second. But wait, where's Joseph? I'm looking in the.
Yeah, that makes a lot more sense. So we don't actually need to like concern ourselves with finding that distance it's traveled up, because that's not something that we need for the equation.
Exactly.
Okay, perfect.
Awesome. No, that's a great question. Okay. That's a great way. I'm going to look at the chat for a second to see if there was but anybody who, well, let me just add, like Pauline, Claudia, Maria, like Shia, you guys are clear on that? Like, you may not have asked that question, but you're okay. All right. So now let me look in the chat. Hold on. But no, that's a great. Wait.
The conversation we were having was trying to figure out when the midterm is coming out. I think that's what you're reading right now.
Yeah, so I'm pretty right. I'm reading the right. So it gets posted tomorrow night. I believe that's what tomorrow's. I mean, I'll check one more. Today's the 20. Yeah. It gets posted tomorrow night by 8. But it's due for class. Yes, it's right. It's due the minute before you walk into class on Monday. So it's like it's due 12:15 on Monday, and you have to come to class that day. I mean, you always have to come to class, but like you really do that day. So technically speaking, if there's any confusion, like technically the exam day is a class day. It's Monday. Like your exam responsibility is to show up and walk in with this. Or I mean, have you just electronically submitted this project that's due that day? But right, I posted tomorrow night basically to give you the weekend. I posted tomorrow night to give you the weekend, and I just tend to, as a tradition, post on Thursday night so I don't ruin your weekend. So, so that if you want so that you have Friday to work on it stuff, and doesn't so that you don't only have your weekend. I mean, there's no particular reason that I posted Thursday, not Friday. It just seems cruel for someone to start their weekend and have an exam pop into their face. So, but yeah, it's due right before class on Monday. But yes, I will post it tomorrow night before 8. Is that yeah, okay. Thank you, Shai. Okay. All right. So the purple plushie question. So if anybody, I'm going to tell you again right now, by the way, my main goal, I have one big problem that I plan to walk through today. It's big, meaning it's a complete problem, but I don't think it takes as long as the one that I did on Monday. And I'm pretty sure that in the other section of 305, I'm pretty sure that I'm going to deliberately do a different problem. So then you have 2 videos you can watch I'll cover 2 more problems in the exam. I'm saying that to say, honestly, I'm pleased on 1,000 levels that Josephine just asked what she did. It was like sort of like the perfect size question. So I want to say there's time for another thing. Like someone else could ask something like that. And now would be a good time. I mean, I'm going to try to do the problem. I'm going to try to do quickly enough so that there's still time at the end. I'm going to try, but you know me. I mean, so if anybody else has something specific like that. And again, I actually think I over talked it. I think she was probably clear, like 5 minutes into what I was saying, but why is there comments on this? Sorry. The screen share is weird. But so if there's other questions of sort of that nature, then that would be great. Okay. I'm looking in the chat. Wait. Oh, interesting. Oh, okay. Oh, I see. All right, someone's asking a very fair question in the chat. And I'm sighing just because it may be hard, but it's very fair. Okay. Someone's asking in the direct chat that there's a bunch of people that, well, I can see why they made it. Someone's asking if I can post it earlier in the day, because it's possible some people may be able to get together and help each other and stuff. So honestly, I think that's a great question too. I mean, I love to hear that people might be getting together and helping each other. I mean, I really love to hear that. And again, for anybody who's unclear, that is legal even once the thing is posted. It's maybe even encouraged. So someone's asking if I could post a little bit earlier. So the most honest thing I can say is I will try my best. The reason that I'll try my best, but I can't guarantee it because I teach a double class at 3:05 on Thursdays. I mean, not this one, a different. And I have 4 other exams to post, so I can't promise, but I will try. But I will say this. I mean, I'll do my best, but I will say again, like, okay, all right. I will try to take that into account because it's so nice. I mean, how could I argue that? I will try. I can't promise, but I can tell you this again, folks, like the differences between what you actually have to do and what this practice exam is saying, the differences are small enough that I promise you, if any of you is getting together with anybody or doing anything, like if you literally were just working on the practice exam, the adjustments you would make would not have to be huge. Like you would still be doing yourself a huge favor. Yeah, I can't say it any better. And especially if you're so responsible that you're doing like work on this, like literally tomorrow or tomorrow night, I really would say to everybody, rough drafts and final copies are such a good idea on this anyway. Then just consider yourself doing a rough draft of the real thing. And when you see the real thing posted, you're not going to have to cross out a million things or throw away. Like you might have to like erase some numbers here and there or something like that. But like, it would still be very worth it. I'm not trying to make excuses, but really, don't consider the moment of posting is not supposed to be some huge dramatic reveal. Like the reveal was when the practice exam was honestly, like, yes, you have to take the real thing seriously and you have to like be sure you don't just copy and paste. But if you're really working hard on the practice exam, you're doing your work. You are working on the real exam. That's the purpose of it. I can't say, okay. Wait, what? No problem. Okay, wait. So there's another question and I will get to the, okay. I forget. Tell me again. Oh, wait. In your frat. That's a fair question. Someone's asking in the direct chat whether you're dealing with this in the Friday lab. And that's a very fair question because like sometimes we do, and you might even for the final exam. The thing is, I don't think you are in this Friday lab because then by that point, the exam will already be posted. And yes, you can still work with each other, but it's a little bit tricky to then be asking the Professor Walters questions about it when it's already out. So I can't, and that goes for me too, by the way, people. Once the actual exam is out, you absolutely can reach out or text me if something's not clear or you think there's an error. So there's a typo or you can't read something or you think information's missing or something. But what you can't do with me or Professor Walters once it's out is say, can you look at my work so far and tell me if I'm on the right track? Like there's 1,000 ways that people always try to do that. And that's a little bit out of the boundaries. So unfortunately, I don't, if Professor Walters does give you help or give you time I won't stop it. I mean, but I don't think we can expect that this Friday, now that when the exam's already out, that you will be spending lab time. I don't think, but okay. But maybe for the final, we'll try to arrange it better. Okay. I'm just looking at, so I will try to post this thing earlier. And again, what I can promise all of you, absolutely promise, is that the real exam is definitely not longer than the practice. We don't add things to the practice to make the thing real. We sometimes subtract. It might be shorter. You might even have choices in it or something like that. But the practice, like the biggest deal of all this, like if you really work through the practice exam, you're set. Okay, I'm going to shut up. So if there, I don't know why this. Okay, I'm changing this.
Professor, I do have one little question.
Yeah.
Can we in part 1B, the one that's based off the big old duck, can you just go over what the difference between like due west and due east mean compared to like just west and just east? Because when doing the diagram, it was like we were kind of having trouble of like, okay, where does this arrow go? Where does this go?
Oh, yeah, that's a great question. That's another really perfect question. Also, I like to hear that you said we. That's great. Like if people were already thinking about it together. Okay, yeah, and I'm looking at it right now, or I think I have it on the screen. Because in fact, I remember something weird. I'm glad you understand that it's, oh, yes. Okay. You understand that it's a big old duck. That's good. Okay. So first of all, yeah, due west and due east. That's not meant to confuse anybody. Honestly, due west just means exactly west. It does mean west. Maybe it's unnecessarily wordy. Like, so if we say due east, we're really trying to say, what we're really saying is 0 degrees east. Because technically all of these directions, right, they're all supposed to be angles plus points of the compass. So like normally you say something like 30 degrees north of east or something like that. So there's usually a number. So the reason I think physicists or people say due east is they're kind of trying to say, when I said east, I'm not trying to be vague. Don't think like, well, where's the number? How east are you talking about? Like roughly east? So when we say due east, we're really just trying to say, we mean exactly 0 degrees, like east. That's all. If that, does that make sense? Okay. But I'm going to quickly look because she's right. I like, this problem for what it's worth, yeah, I have mixed feelings about the way this problem is worded, and we might change some of the wording for the thing. I mean, clearly, it says the central question in this problem, in this Roadrunner problem, where you'd want to show your most work and really use your diagram and really explain everything is D, right? It's really all about D. The questions A, B, and C are kind of like helping you set up and I'll even just say right now, as long as I'm looking at just to be, wait. I think there was something else about this problem. She's right. I remember there's often a wording concern that people have. Oh, wait.
If it helps, the main reason why I asked that question is because it mentions that the Roadrunner is west of the cliff, but it's traveling east. But then it later says that it begins accelerating west, and we weren't sure if that meant that it had turned around at a certain point.
Oh, okay. No, that's good that you're saying that. Okay, hold on. Okay, that's a great question too. That's a great question. And it's kind of like Josephine's question. Okay, so that's not, so first of all, it's not a typo or an error, right? It does mean what it's saying, but okay, no, accelerating west while, let me back up. So she's right. I mean, Maria's right to notice, is it Maria? Yeah, Maria's right to notice that if you draw the picture and if you draw the diagram and you try to picture it, the Roadrunner certainly is traveling to the east. Let's say on my piece of paper, east is to the right. So the Roadrunner is definitely velocitizing, moving that way. But when it says she's accelerating the other way, it doesn't mean that she has turned around, does not mean that she has yet turned around or anything. It doesn't mean that she did something weird. It means that the direction of her acceleration is opposite to the direction of her velocity. I mean, so that means a couple of things. And that's totally can happen. This goes back to homework number 4 or 5 or something. It means a couple of things. First of all, let's say we're calling the direction right positive. Like, I guess it has you be very specific about, okay, it's like forces you to put in your pluses and minuses. And again, by the way, you always need to do that anyway. This problem is kind of like getting very picky and making sure to give you instructions to do things that you're always supposed to do anyway, because it's kind of calling attention to the fact that you really have to be careful about those things in this problem. And like, that's why Maria is asking. So say you have labeled to the right as positive, which is a good idea, and you labeled left as negative. Then first of all, what this is saying is her velocity is positive, but her acceleration, not Maria's, I mean the Roadrunner's velocity is positive, and the Roadrunner's acceleration is negative. Now that's not a contradiction. That's a total possibility. Let me give you 2 facts about that. Number 1, that is literally like saying in Josephine's purple plushie problem, that's like saying a purple plushie has positive velocity, but it has negative acceleration. It means it's accelerating in the opposite way from the way it's moving, which means the velocity numbers right from the get-go are getting smaller and smaller. They're decreasing. The velocity numbers are decreasing. So it means that if right now the velocity numbers are positive, say right now, in fact, I think does it tell you? I can't remember if that's what you're trying to solve for, or no, I guess that's what you're trying to solve for. Wait. Oh, no, it does tell you, yeah. So right now, the Roadrunner's velocity is positive 25, let's say, positive 25, right? But her I don't know why I'm saying it's her, whatever. The Roadrunner's acceleration is negative 5, right? So what that means, so I'm kind of giving away the whole problem explaining this right now, but fine, good. That means every second, the Roadrunner's velocity is going down by 5. So her velocity numbers, and again, this is not an example, like I'm literally telling you because it's a good question. Her velocity its velocity numbers are going 25, like positive 25, positive 20, positive 15, positive 10, positive 5. I mean, if we were let it go on forever, it'd go positive 5, 0, and then negative 5, negative 10, negative 15, right? So in other words, if everything keeps going forever as the facts are presented, this Roadrunner would go forward to the east for a while, but eventually hit 0 and then start coming back. I am saying, and I'm going to say one more thing about it and then check in and make sure we're okay. And we still are fine on time. And the problem, again, in my mind, these questions could not be more like worth it. Especially because this one's like generating half the answers to the problem, if you're paying attention to what I'm saying. I'm saying it's not that the Roadrunner right from the get-go did something weird and like started going backwards or something, but it does mean that, oh yes, if it always is true, if your acceleration is in the opposite direction from your initial velocity, what that means in English is you're going to slow down for a while. You're losing your velocity. The acceleration is contradicting or opposing your velocity. So you're going to be losing velocity magnitudes for a while until you get to 0. And then definitely for sure, you're going to turn around and come back the other way. Whenever in any problem, the acceleration is opposing the velocity, that's basically saying I'm changing you to eventually flip the other way. And what I'm really saying by all this, if you're following me, if Maria's following, or if I haven't lost everybody already, this is what I really mean. When we say that this problem is really the Roadrunner kind of like flipped on its side, flipped on its side, we really mean it. Like the acceleration velocity, the type of motion that the Roadrunner is doing right here is a direct analogy to what happens when you throw something up in gravity. Then necessarily right from the start in gravity, like the purple plushie, right? If you throw something up, then you're giving it a velocity that's in contradiction to the acceleration. So they're in opposition to each other. So eventually the object stops going up. I mean, it goes slower, it hits 0 and it starts to come down. That's literally what's happening to the Roadrunner here. If the Roadrunner's acceleration is constant, really truly constant, like the acceleration doesn't change, that means the velocity numbers will change in a pattern that will eventually bring the Roadrunner back in the other direction. That's totally what it means. Now, wait, I'm going to pause for a second. So first of all, Maria, does that make,
that makes complete sense, yeah.
Cool. I like the complete. Oh, that makes me happy. All right, cool. And I totally see, by the way, secret shout out to people. Video is not required, right? It's totally not required. But like this is why video is so good, because in a moment like that, I actually feel like there was communication. Like I actually think that she does get it, and it really helped that I could see her face. I'm just saying, it just helps you in the class if you're occasionally like really with me. I'm just saying, but okay. But anybody else if anybody want, I'm looking at the time. Honestly, I'm telling you, I would not lie. Well, I would by accident, but I am going to walk you through a full problem. But now these questions have been so good. One person just like helped everybody. If you're listening to one of the exercises at the beginning, another person's question, just if you really were listening to her question and my answer, like in a way, I just gave away half the answers to that Wild Coyote problem. Like I didn't So we're covering a lot of ground in this test. And I'm going to tell you right now, the one I'm going to do with y'all is the one that's on the screen right now, without a paddle. So we're actually, and in the other class, I'm probably, like on the other video, I'm probably going to do this one. So we're covering ground here. So if anybody wants to follow up on Maria's question, oh, chat. Okay, there we go. Okay. Oh, okay, cool. Oh, well, I love this class. It's so sweet. I feel like I could retire right now. Forget this exam. Let's just have a retirement party. No, I appreciate it if that does. Okay, good. So so I'm going to pause for one. I'm going to just give a beat. So you see the role model, and I mean the model now. If anybody else has a question like that, that's like about a part or a thing, this would be a good moment. I'll just pause. But other than that, but I'll also set up. If not, we're doing the thing that's on the screen right now. Oh, okay. I'm just going to wait for a second. I'll even check. Okay. I think, okay. I'm going to assume that's okay. And not that you can't still, I mean, and again, okay. I'll just get to it. Okay. So so we're looking at this one now, like screenshot it if you need to, whatever. This is a good example of this one, by the way. I'll just tell you right now, like, since I'm going to talk through, this is one where almost definitely I do change the numbers on the real thing, but that's about all I changed. This is like a classic problem that I did not make up. I mean, most of these we made up, but this one's sort of a famous historic problem. It's sort of hard to mess with other than the numbers. But this one also going to say right now, because I'm talking about without a paddle. This one is like, there's math to do and stuff, but I'm warning you right now, the whole key of this one is, this one really is to really make sure we really understand and take seriously the concept of relativity, like train of thought. Like, so this is really an example where the concept thread of this class and the math thread of this class like really come together in a way that you'll either find like, oh, okay, I guess this isn't all random material. I guess it all does connect, right? Some of you will think, and then some of you will be like, oh my God, no, I totally, like, I hate this. Like, what I'm really trying to get at is, I'm going to do it for you right now, but I'm telling you that the purpose of this problem is that the purpose of this problem is not to do a bajillion equations. You could solve this problem with a bajillion equations. You could, and you can get the right answer. You could do a lot of hard algebra and get the right answer to this question. And then it would be a really like good math question. But it's actually meant as a physics question. Again, I'm looking this without a paddle thing. It's meant as a physics question. So I'm going to tell you right now that if you get the physics insight of it, if you actually see the physics that we're trying to say, and you make a good choice about how to set up this problem, then you will find that you don't end up having to do a lot of math at all. The math is like 3 lines, and that is the physics demonstration here. So that's the good news, that if you follow what I'm about to explain, there's not a lot of hard math at all, and not a lot of hard equations. That's the good news. And it's sort of trying to show the power of physics. But the bad news, or the warning that I'm giving you right now, is assuming this is on your exam, or assuming like assuming you do this on your exam, you really have to go to pains to explain to me whatever it is I'm about to explain to you right now. Like, this one's very easy for people just to copy the 3 lines of math and think they've solved the problem, but they don't explain it well. And it's here you really have to explain, you really, in words and pictures, you'll really have to show me that you know why the math is math. So that's where I'll try to, when I get to the point in it, I'll even show you like the place where people always, where people often like leave out explanation, but just be aware of that. All right, so I'm gonna switch screen. Well, all right, so here's the problem, right? I mean, you're looking at it. It's a lot of reading. Just to be clear what the problem's saying, and then I'm going to switch screens. Like, there's this river, right? And it's flowing. So whenever we say upstream or downstream or whatever, and again, I give you the picture here because it's a complicated enough problem that we should make it clear to you, but do not be fooled. You need to draw your own picture, and probably you're going to draw more than one picture to do this one right. But you certainly have to start with your own picture and try to take the key information and make it clear. So the situation is that there's a river, and it's flowing, like there's a current in the river. The river has some velocity relative to the shore, relative to the riverbank, if you like, relative to the land, right? The water, if you were standing on the land, you would see the water flowing, right? And whatever that direction is that the water's falling, we call downstream, and we make it look like that in the picture. Like, so down on the page is the direction of the water flow. Okay, and then there's this bridge over the water. The bridge is stuck to the land. The velocity of the bridge relative to the land is 0, like on purpose, as you would expect of a bridge. The bridge is there to be used as like a reference point. The bridge is a reference point. A reference to what? Reference to this. You've got this boat, or you're in this boat. You're somewhere below the bridge. You're paddling the boat, so you're going upstream. Like you're paddling hard. If you didn't paddle at all, the boat would automatically have the same velocity as the water, and it would travel with the water downstream. But you're paddling. So the boat has some velocity relative to the water. When I start solving the problem, I'm going to call that like VBW or something, velocity of boat relative to the water. So the boat has some velocity relative to the water. I'm just looking at the time. And I don't know what that is. And it could be really tiny, right? It could be 1 mile an hour. As long as it's not 0, that means the boat is going up the water. As long as it's, right? So as soon as we get to under the bridge is just a reference point. It's like where the experiment begins. It's like someone starts a stopwatch right when the boat is on the bridge, and you drop a soda bottle or like some kind of bottle, out of the boat. The boat keeps going, doing exactly what it was doing before. But the boat and the bottle are now separated. So the bottle is going downstream. Definitely the bottle, it now has the same velocity as the water. Like the bottle is now in the reference frame or the perspective of the water, for sure. The velocity of bottle relative to water is 0, which means the velocity of the bottle relative to the land is some number that I don't know. It's whatever the same number is that the water has, okay? But you're going up the stream. When you get 20 minutes above the bridge, you realize that you've dropped this bottle, right? So you turn around in a really short amount of time. This goes back to Josephine's thing now. Like you turn around and we're going to say we imagine the amount of time you take to turn around is so small compared to all the other dimensions of the problem that we neglect it. This is a case where I don't care about the turnaround. I just know that 1 instant later, the boat is now coming back to retrieve the bottle. And the one key fact that we're given, we still don't know what the speed is of the boat relative to the water, but we know that it is the same whether the boat is going up or down. I'm not saying that's always true about boats and waters. That is not like that's not a physics law. We're just saying it in this problem. It's a given in this problem that if the boat was going 1 mile an hour relative to the water on the way up, then the boat is going 1 mile an hour relative to the water on the way down. We're just saying that. And so the boat starts coming down to retreat. So the water, that means the boat is now traveling downstream. If you think about it, necessarily, if the boat has velocity relative to the water as it's going downstream, that means it's going downstream like faster than the water itself. It has to be. So the boat will eventually catch up to the bottle, right? Because the bottle is just floating in the water. The boat is paddling. You are paddling the boat. So the boat eventually does catch up to the bottle, but the fact that we're given, and I'm just about done explaining, is that catch up occurs, or that intersection occurs 1 mile below the bridge. Okay, that's the scenario. And the question based on those 3 weird facts, is how fast is the water going relative to the shore? Like, what is the speed of the current? That's the question. And I'm going to solve it now, obviously. But notice I just said the question based on those 3 facts. I mean, I guess there's sort of other facts too, I guess. But I think there's 3 key facts that the problem's giving you. One is that the boat goes 20 minutes above the bridge before it turns around. I think that's a key fact. 2 is that the boat goes 1 mile below the bridge before it catches the bottle. That's a key fact. And the other key fact is that whether the boat is going up or down, the speed of the boat relative to the water is the same. That is a key fact. Like, it has to be said, because it would not, because it can be true, but it certainly does not automatically have to be true. And the fact of it being true is necessary to solve the problem. I promise you that. So, okay, so I'm going to solve the, all right, so people with video, like, the question is clear, right? Yeah, okay. So the question is, what's the speed of the water relative to the shore? Okay, so here we go. I'm just switching screens to do this. And what's it called again? It's called Without a Paddle. Okay. Oh, okay. Well, and one big hint, okay, by the way, the equations on the board right now are a big hint for this. They're not really new equations, but just notice the first equation, like GPR form number 4, case number 1, seems like super obvious, and seems like one of the things, like, how do we ever use that? We're going to use it right now. That thing that it says there on the board, VAA, triple equal sign 0, what that means in English is anything is at rest to itself, right? Anything is at rest to itself. Any perspective can be, as long as it's not accelerated, any perspective can be used to look at the world and watch everything move. Anybody can be first person. Anybody can view themselves as at rest and watch the rest of the world go by it. The Earth frame of reference, put it one last way, and I'm going to use it right now in the problem. I'm not just babbling. I mean, I am babbling, but like, a key way of understanding that, this whole Galileo thing, is what we're really trying to say is, in the end of the day, the Earth perspective, looking at things, looking at the world from the perspective of the ground or the Earth, is often convenient, but that's it. It's just often convenient. It's not always convenient, and it is definitely not objectively true. Looking at the world from the perspective of Earth is not special. It's no better than looking at the world from the perspective of Jupiter or the sun or a flowing river, for example. All perspectives, as long as they're not accelerated, all perspectives are equally true. That's why video games work, right? So we, in physics, because all perspectives are equally true, because we have a choice, we make a choice. And in physics, the physics trick, the physics insight, which I'm about to use right now in this problem, is we pick the perspective that is the most convenient, that makes the problem solving most straightforward and direct. That is not always planet Earth. And then the thing, that's what I'm about to show you or do. And the thing right underneath it, I don't know if it looks like a new equation to you or not, but it's just emphasizing, remember, our key equation for this whole class, like our first thing ever that we said, is an average velocity equals displacement over time, right? And everything sort of comes back to that. Now I'm just saying, well, in math, all our math equations, we've been using average velocity equals displacement over time. When in doubt, that's always like the first thing we write down, because it's like always true. Now I'm saying, well, the conceptual thread in this class is that velocities are always relative. So I'm just saying, from here on in, make no mistake, the relativeness of velocity is, we apply to all the equations that we have and all the knowledge we have about velocity. So in other words, at any moment now, we could put a couple of subscripts on any equation we have, and sometimes we really should, because the velocity of me relative to you is as valid as the velocity of me relative to the Earth. So the velocity of me relative to you is the displacement of me relative to you, et cetera. I'm just, that's a way of just saying that all of these ideas actually relate to each other. Okay, so to go to the problem, this is without a paddle. To cut straight to the chase. Okay, and I'm talking, as usual, way too much. I'm going to do it. I'm telling you right now, anything that I write down on my page, or you want to expand a lot more in your version of this problem. Like, I'm talking a lot, maybe replay the video. It's what I'm saying that you're going to want to write down in the problem. I'm going to write a limited version of it to make sure we get through it. But like, so I'm going to say, well, okay, so I have the diagram, right? Here's the bridge. I'm just doing what you would do, like we would draw a diagram and all that. Label everything in the diagram. Okay, and in my diagram, I'm going to say something like, let W equal water, let S equal shore, let B equal let B equal boat. And then to be as clear as I can, I'm going to say let C equal can, and let the bottle from now on be called a can. I'm just doing that right now. I mean, the problem says bottle. I'm saying from now on, I'm calling it a can, just so that I don't confuse B for bottle and B for boat. You can do that too. I'm just saying from now on, the bottle is a can. Okay, just to make the notation clear. What else do I? Okay. So that's my diagram. You have to label it more clearly than that. I'm just trying to watch the time, but that's my step one. Approximated. Okay. And then step two, of course, is the question. And the question is, what is the velocity of the water relative to the shore? Right? That is the ultimate question. The velocity of the water relative to the shore. So step three, here's the key now. And let me tell you again, too, if you're still listening, I mean, I'm trying to make sure I get to the point here. And I don't want to get bogged down in the diagram, but in your step one, you definitely have to write down those three key facts. Like they have to be in your, like the 10 minutes or whatever, the 20 minutes, those numbers, but also somewhere, like, I don't want to fool you, somewhere in your diagram for sure, you have to make it clear that the speed of the boat relative to the water on the way up equals the speed of the boat relative to the water on the way down. Like that, I guess whether this is a hint or you got to include that key point in your fact pattern in the step one. It is the key to the whole problem. Okay, so make sure that's there. And step two is, what is the speed of the water relative to the shore? Now, step three, what's step three? The GDP here. Now I'm going to start switching. The GDP is Galileo's principle of relativity. Write it out. Okay, I'm abbreviating, but write out the Galileo's principle of relativity. And the more you can say about it right here, the happier I'll be. You may want to write form number 1 and or 2 or 3 in words and make sure get across to me that you understand. So I'm going to give an abbreviated version here, but like all velocities are relations between pairs of objects. Another way to say it, like all velocity, every velocity is measured from a chosen reference frame no reference frame is more true than another. What I'm doing right now, notice this, of course, my handwriting is hideous. Please note what I'm doing right now. I'm trying to give you an example of what you would do in your exam. Do you notice that what I just did was you would write down one of the forms of GPR or maybe many of them or whatever, but then notice all of a sudden I'm summarizing the point of Galileo's principle of relativity in new words now. And I'm not doing this to confuse you. I'm doing this to give you an example of what you would ideally do in the exam. You would understand Galileo's principle of relativity enough, and you would quote it, or you'd put a form 1 or form 2 or whatever. But then in your own words, you would sort of take away what the takeaway is. And I'm giving you an example now of new words for it. The takeaway is like whenever we're measuring velocity, we're doing it from a perspective. And one perspective is not more correct than another. They're all equally correct. The laws of physics are the same in all of them. And why am I saying all this as my GDP? Because what I'm going to say right now, with 25 minutes left, if I really understand relativity, and I understand it's saying there's no one correct way, there's no one correct perspective in the universe, it means to me, thus, and this is now I'm moving into step 4, PAW. Thus, here in this problem, it is most convenient to solve the problem. Well, I'm going to say, but you've got choices here, right? We could solve the problem from we've got 3 objects. We've got a shore, we've got a river, which has a bottle in it or a can in it, and we've got a boat, right? That's 3 different objects with 3 different velocities. That's like A, B, and C, right? Boat, water, shore. Any one of those velocities any one of those perspectives is as correct as the others. If we don't think about it at all, if we don't choose one, no, let me start again. According to relativity, you've got to choose a perspective. Until you know about relativity, you don't know you have to choose a perspective. You think you're not choosing a perspective, so you just start solving the problem. But what you're doing, if you don't make a choice at all, you're tacitly solving the problem from the perspective of the shore, from the earth. When people don't think this through consciously, they just observe things as though they were standing on the shore, on the earth, because they're used to doing that and they think it's like the correct way to do things. The shore is one possible perspective to observe this problem. But I'm saying there's 2 other possibilities. We can look at it from the standpoint of the boat, or we can look at it from the perspective of the water, or the can that's in the water. And I'm going to choose that one. I'm going to choose, it is most convenient to solve the problem from or in the reference frame of the can, which is in the water. Okay, so if again, those of you who like the whole video game analogy, we are now the can. Like, watch the problem in your mind. Take a movie of the problem in your mind, from the can's perspective. And the can's just floating in the water. The can is doing whatever the water's doing. They're one and the same. So picture yourself as like a little water molecule, if you like, or a little lily pad that's floating next to the can. From in the can water reference frame. Again, I'm calling it can just because I'm worried that if I call it bottle, the B of bottle and B of water will get confusing there. So I'm calling it a can. In the can water reference frame, in the can water reference frame, in the can water reference frame, we see, or we observe a boat, travel upstream for 20 minutes. Right. We see a boat travel upstream for 20 minutes. That much we know, right? Hopefully you're with me. If you're the boat, if you're the bottle, well, from the bottle's perspective, if you're the bottle, right, you just separated from a boat like just dropped you. A boat is starting to move away from you now. The boat's going up for 20 minutes. Also, a bridge is going up, right? The entire shore is going up from your perspective, right? Like you're just a bottle. You're looking at the world. If it were a video game, you would see the bridge and everything it's attached to, the whole shore like receding up from you, because from the perspective of the bridge, you're going down, right? So you would, and you could explain this like in terms of, you could write in your thing on the test, you could write like, this is all what I'm talking about right here is this. If we all believe, and I am watching the time, I promise, if we all believe that from the Earth's, from the shores, from the bridge's perspective, a bottle is going down, well, that means from a bottle's perspective, a bridge and a land next to, like, some people are having a picnic on the land over there and you're the bottle, like you're seeing those picnic people go up, up, up away from you. If the river is flowing south, you're seeing them go to the north, right? You're also seeing a boat go to the north, going up, and the boat is going up faster than they are, right? If you were taking a movie of this with your movie camera, I hope, stop me if you don't agree, but the bottle sees everything moving up away from it, and it sees the boat going faster than the bridge. And it sees that for 20 minutes, right? Maybe that, hopefully that's not so mysterious to you, but now here's the key. If we're really looking from the bottle's perspective, right? After everything goes up for 20 minutes, then the people in the boat discover that the bottle's gone. So we know the boat starts turning around, right? I mean, it does turn around and it starts coming back to us. Well, after 20 minutes, the bridge continues to go up, right? The bridge and the land and all that continues to go up away from the bottle, continues to go up. But now the boat is coming down, right back to the bottle. Now we don't know what this, and I should have said, after the boat has traveled up for 20 minutes, that we know, but some unknown distance. We don't know. We don't know how far the boat went up compared to the bottle. Like compared to bottle. I don't know how far away the boat is from the bottle when it turns around, but I do know this. However far it went, and I'm talking about the boat now. Like the bridge is also far away. They're two different places, right? The boat is like way above the bridge. They're both ahead of me if I'm the bottle. Like there, I look up there, there's a bridge and there's a boat way up there. And by the way, again, I'm trying to save time here. So I would recommend that you draw different pictures at different stages of this to make clear. Anyway, I look up, I'm the bottle, and I see the boat way up there. Now the boat starts coming back down to me. I don't know what that distance is, but I know this. If I'm the bottle watching all this, whatever that up distance is, that the boat just did, it's going to come down to me that same distance. This is absolutely key. This is what you guys are going to, if you're getting together Thursday, any of you, I promise you this is on your real exam, whether or not the darn thing is actually, this is the part you want to talk about. Because some of you will believe what I'm about to say, some of you won't, but the majority of you will sort of believe it, but then every time you think it through, it'll bother you. Like you won't know why, but it'll bother you, and you want to talk about it with each other. Here's what I'm saying. I'm saying this. Wait, oh, now I keep calling it the bottle instead of the can. And I apologize to every, no, I'm not. Okay, from our can water perspective, reference frame, whatever distance the boat went up must be the same as its down return distance. I'm going to say this one more time. I know we've got 14 minutes. Now think about this. You're going to want to draw pictures. It's sort of sound. There's many of you probably who, if you're listening to me, think what I'm saying is so obvious. You don't know why I'm making a big point of it. But when you contrast it with something else that may be somewhere else in your mind, it's weird. I'm saying if I'm the bottle, if I'm a water molecule watching the boat goes up and then it eventually comes back down to me. So from my perspective, something just made a round trip. It went away from me, it came back. The two distances have to be the same, whatever they are. If you run away from me 3 miles, then to come back to me, you got to run 3 miles. I mean, assuming everything is straight, which everything is straight here, right? From the bottle's perspective, whenever the boat went up, the boat came down. Now, the reason I keep saying that that's a huge point, and it is a huge point, and the reason I'm warning you that it's confusing once you think about it is that's from the bottle's perspective. Of course, if you're standing on the shore watching this whole thing, as people would tend to do if they don't know about relativity, if you're just standing on the shore watching this whole thing, then the boat goes up some, like if you look at that diagram, the boat goes up some unknown distance above the bridge, right? And then it comes down and eventually hits the bottle somewhere way below the bridge. So if you watch from the perspective of Earth, you see something like this, kind of like the Josephine thing again. You see something like up some bit and then down a much bigger bit. Like they're not equal distances if you watch from the Earth. This is how you'll know you know what I'm saying. From the perspective of Earth, this distance is unknown and this longer distance is also unknown, and they're different. That's a lot of unknowns to deal with in the problem. What I'm saying is if you're the bottle, if you're watching from the bottle, you see a can, you see a boat go away from you, and then a boat come back to you. End of story. When it comes back to you, sure, you're way below the bridge now. Put another way, when it comes back to you, the bridge has also moved up the whole time, but you don't care. That doesn't have anything to do with the, right? Like you see something symmetric. Boat away, boat back. While the whole time a bridge is gone away, right? In other words, you could say you're down here by the time you retrieve the boat, but that doesn't have anything to do. You don't care. You don't think you're down anywhere. You observe the bridge being up above you, and that's valid. So the bottle's perspective is most convenient, and I am almost done, believe it or not. Like this is the heart, and this is the thing you have to explain anything. There's no numbers here, there's the words. The reason I'm choosing to solve this from the bottle's perspective is, or the can's perspective, is that is the one and only perspective where I cut down on unknown information, where I could say, wait, from the can's perspective, a boat just made a round trip. It went away, it came back. So I don't have two unknown distances, I just have one unknown distance. And that is only true from the can's perspective, but all perspectives are equally valid. So if you think about that, or you accept that, or you explain that well to me, then therefore, that means, sorry. And so that's true. That's true from the can's perspective, no matter what. But since we were also told that the velocity of the boat relative to the water, i.e. relative to the can, on the way up is the same as the velocity of the boat relative to the water on the way down, since they're the same? Well, think about this now. And we have 10 minutes left. Think about this. The boat went up, the boat went down from the perspective of the can. If the boat went up, the boat went down. Two identical distances. Well, we were also told that whatever the boat is doing relative to the water, relative to the can, we were told that the speed up is the same as the speed down. So since the speeds and distances are identical, since the speeds for up and down and distances for up and down are identical from of the boat, from the perspective of the bottle. Like, wait, I'm going to write it again. From can water perspective, I'm saying VW, I'm saying VBW up equals VBW down, and X or Y, if you like, whatever. Y BW up equals Y BW down. The velocities, the speeds, and the distances are the same. Therefore, time up equals time down to the can water. So the key, now this, again, everything I'm saying should seem simple. It's not a lot of like detail, right? But it's only simple and it's only true because I'm looking at it from the can's perspective. What I'm saying again with 7 minutes left, I'm saying if you're looking at it from the can's perspective, you just see a boat go, it goes up a certain distance, comes down a certain distance, and it goes up at a certain speed. From your perspective, right, relative to you, because you're the water, and the boat's always doing the same thing relative to the water. And let me say again, sidebar, that means the boat is not always doing the same thing relative to the shore. The boat must be going, the boat must be going much faster on the way down. If you're watching from the shore, the boat is struggling against the water. Maybe it's going 1 mile an hour faster than the water speed. So it's just barely beating the water and just like inching up. If it's going 30 miles an hour relative to the shore, while the water is going 29 miles an hour relative to the shore, the boat is just barely advancing from the perspective of the shore. Then it starts coming down, but it's still going 1 mile an hour faster than the water. So now it's zooming down at 31 from the perspective of the shore, right? So you see a slow moving boat and then a fast moving boat from the shore, and you see a boat that goes up a little ways and then goes down this huge ways from the shore. But so that's complicated. But from the water, you just see up, down, same speed, same speed. So from the water, it's easy to see that the up time must be the same as the downtime. Now, by the way, that time is time. That's also true from the shore. From the shore, it's a short distance and a slow speed, and then a long distance and a long speed. If you're really getting what I'm saying, you might want to throw that into your explanation too. From the shore, it's a short distance and a slow speed, and then a long distance and a fast speed. So it still works out to be same time, but you can't, but to figure that out or to prove it or to know it in advance from the shore is impossible. From the water's perspective, we can see, up distance, down distance, same, up speed, down speed, same. So times have to be the same. Therefore, therefore, it's also 20 minutes back back down to the bottle, to the can, to us, right? It's 20 minutes that we're separated and then 20 minutes to be reunited, right? 20 minutes back to the can. Thus, whole round trip takes 40 minutes. That's what I've just figured out. Whole round trip, or the whole experiment, takes 40 minutes, 20 up, 20 down. I could never have, it would have taken me a lot of math to realize that from the short perspective. I would have realized it because physics is physics, but it would have taken a lot of math. And now, am I done with the problem? No, I'm not done with the problem, but I have one step left to do, and then I'm done with the problem. It seems to me the whole round trip takes 20 minutes. During this 20 minutes, I'm sorry, 40 minutes. During this 40 minutes, from the perspective of the bottle, from the canned water perspective, we observe during this 40 minutes, a bridge goes up, a bridge which is attached to the shore, right? The bridge goes up, a bridge, right? So we're the bottom, and again, the more you can draw this, the more you can put this. You notice I've taken like 5 pages to explain this already, but I'm just like scrawling my way. You don't want to scrawl you get what I'm saying? Like, this is now just me. You want to do your version of laying this out once you get it, and you will have anyway. I'm saying this: what if I was the bottle and we got 3 minutes, and we're on the last step. I just want to make sure you see it. If I'm the bottle, I saw a boat go up and back to me and take 40 minutes to do that. That's like what I've just proven so far. If I'm the bottle, I see a boat go up and down and come back to me in a total of 40 minutes. Like, I've now used 2 pieces of information. I used the 20-minute information, and I found out that, 20 minutes was literally half the trip. No way am I saying I saw that at the beginning of the problem. It wasn't a given. The problem did not say that the whole experiment takes 40 minutes. The problem says that the boat turned around in 20 minutes. But I just did a bunch of thinking to realize, well, if the boat turned around 20 minutes later, then I think the entire experiment took double that, took 40 minutes. So I've used the 20-minute fact. In order to say that the 2 times are the same, I absolutely used the boat is always going at the same speed relative to the water fact. If I didn't have that fact, I could not have said that the whole experiment takes 40 minutes. So here now, I'm just going to use the third final fact of the problem. The entire experiment took 40 minutes. During 40 minutes, a boat went away and came back to me, the bottle. During that time, I just saw a bridge continually going up, right? The bridge never turned around. Like, I'm always falling below the bridge. The bridge is therefore always falling up away from me. During this 40 minutes, the bridge went up away from me. How far? Well, apparently, according to the problem, the bridge went up away from me 1 mile. 1 mile. Where did I get that? If you look at the picture, when the problem's over, the bottle is 1 mile below the bridge. That means when the problem's over, the bridge is 1 mile above the bottle, right? From the can, whatever. From the water's perspective, a bridge traveled up a mile, a bridge and everything that was attached to it. An earth, people picnicking, I don't care. And I don't care. The bridge went up, the bridge goes up 1 mile. 1 mile. So during this, and we have 1 minute. So from the water's perspective, therefore, the speed of the shore relative to the water is 1 mile per 40 minutes, right? That's what it is, which is to say, in other words, 1 mile over 2/3 of an hour is what I'm saying, right? 40 minutes is 2/3 of an hour. So that means 3/2 or 1.5 miles per hour. The speed of the shore relative to the water is 1.5 miles per hour up. Therefore, the velocity of the water relative to the shore is 1.5 miles per hour down. That's relativity. And that's the answer. The water must be going at 1.5 miles per hour relative to the shore, relative to the bridge, because the bridge is going up at 1.5 miles an hour relative to the water. We did the problem from the perspective of the water because we really believe relative. And I'm telling you, and this is my last thing, if we had done from any other perspective, we would ultimately have to get this same answer. Physics is physics is physics. The other perspectives are equally correct, but they're just not as convenient. It would take us a lot more math. So that's it. Okay, so we're done. So thank you for being so patient. I'll try to post the thing as early as I can. I will try. I just can't promise. But certainly it'll be okay. But have a great yes. Oh yes. So I'm hanging. I'm not going anywhere. Yes. Yes. I mean, if there's questions, I'm here. Hold on. Let me just. I'll turn off the recording, etc. But yes, have a great day. Have a great day. Okay. Hold on. Just turning off the recording.